Hi everyone, my name is Fadnavis and I'm a PhD student at Indiana University, Bloomington. In this part, I will be covering Intravoxel Incoherent motion and optimization involved in solving these nonlinear inverse problems. What I'll be specifically covering is what is IVIM. In the optimization part, I'll be covering the variable projection method and topological optimization, along with the method that we are proposing. And in the last part, I'll talk about its implementation in DIPY. All right, let's take a look at what is IVIM. IVIM, that stands for Intravoxel Incoherent Motion, was defined by Daniel Bihan in his 86 paper as the translational movements within a voxel that at measurement time represent a distribution of speeds and orientation and amplitude. So IVIM is basically a method to estimate perfusion in tissues, which and to capture the blood flow information in randomly oriented capillaries, which mimics a process similar to diffusion. The idea is that since they occur at similar scales, they could be confounding as one process could be confounding the other, and we want to kind of distinguish between the two processes. Over the years, IVIM has become its own field. It is often known as IVIM-MRI, and it is FDA approved, clinically viable. It is often used as an alternative to other methods such as arterial spin labeling, gadolinium-based contrast imaging, etc. IVIM therefore stands at an intersection of diffusion, perfusion, and bold fMRI. This is often used in functional diffusion MRI, which is a growing field of its own. So let's take a look at what is exactly going on. So diffusion is a random process. It is Brownian motion of a water molecule. We are trying to capture Brownian motion of water molecules, and that is at different speeds. It occurs due to collisions in random directions. The displacement caused due to diffusion is of the scale of 1/10 of a nanometer, and the mean velocity is 100 meters per second. And it is given by Einstein's diffusion coefficient, 10 raised to power minus 9, and the average diffusion length is around 17 micrometers. The collective motion, we often try to model it using a Gaussian distribution, as you may have seen in DTI. And the ADC is given by the diffusion curve and the exponential decay as the B values increase. Perfusion, on the other hand, that is trying to capture the blood microcirculation, is also a random process, but it occurs in the geometry of the vessel network where the blood circulates. So this is an example, like a toy figure that I wanted to give to get the message across. And the randomness occurs due to the blood flowing in the capillary segment. So in these small little segments that are randomly oriented, that's where the perfusion occurs. And the collective motion is also random. So it can often be confounding the diffusion in a diffusion acquisition. This collective motion is often known as pseudo-diffusion, and we try to model it, and we try to refer to it as perfusion. It occurs at the scale of 10 raised to power minus 8 meters square per second. The average length is 100 micrometers, and the mean velocity is 100 millimeters per second. So you can see this process is much faster. It occurs at 10 times higher scale, but they are more or less similar and can be acquired by the same acquisition. So this is what IVIM, this is what the standard IVIM model looks like. So let's say this is the ADC curve that I showed on the previous slide, where we are trying to model the exponential decay. In a standard diffusion acquisition, we have a set of B values that are generally on one shell, like 1000, or in a multi-shell it has 1000, 2000, 3000, and so on. But for IVIM, we require a lot of small B values. So generally in the scale of less than 1,000. So generally we acquire a lot of samples that are at a b-value of from 100, 200, 300 to 1,000. And around 400, that is where the less than b-value 400, that is approximately where the perfusion process begins to confound the signal, and that's where IVIM signal is modeled. So this is the data space. It is modeled as a bicompartmental model. Both are isotropic. So F is the volume fraction, like how much of that voxel was corresponding to perfusion and how much was it corresponding to diffusion. This is the ideal acquisition that we try to hope, but obviously there is some noise. The noise is not, like right now I've just pushed the points away to show that they are not along the ideal acquisition. And what we are trying to do is approximate this curve in the model space. And in the model space, since it is noisy, you kind of get pushed away from the ideal approximation, assuming that the model was correct. And this is what happens. So this is the figure that I've plotted for showing the difference between perfusion and diffusion. So diffusion is modeled by a Gaussian distribution, and within this Gaussian distribution, you have these water molecules that are colliding and randomly moving around. And this is like an example movement of one molecule. And this is what diffusion at 10 times higher, like a perfusion, would look like. And they kind of get intertwined with one another. And we are trying to basically disentangle these effects using the IVIM model. So IVIM, like I mentioned in the previous slide, is modeled as a bi-exponential. By bi-exponential, I mean that you model one compartment for diffusion and one compartment for perfusion, and they are a convex combination. So whatever does not contribute towards diffusion would contribute towards the perfusion process. And they are like in the exponential, you have the b-value, and this is the S0. Over the years, many different models for IVIM have been proposed. So the more famous ones I have included in the slide. So this is IVIM with D blood. So it is hypothesized that this D star is actually an effect of two different types of processes. One is due to the blood. It is often referred to as DFAST, like diffusion of the blood. And that is along with this perfusion process. And the other one is IVIM with the DKI, where we know that diffusion, by modeling that as a Gaussian, like a single tensor, is often like not correct and has its own limitations. And therefore you can have a kurtosis component in here to get like DKI kind of effects to understand the non-Gaussianity of the IVIM that we're trying to model. And of course, you can put these two together and get a model that basically has the D blood and the kurtosis compartment in there. So this problem is like estimating IVIM is an ill-posed problem. Well, what Hadamard said, that what is a well-posed problem is that you would always have a solution. So for IVIM, we do always have a solution, but there is no uniqueness in the data since it's like a symmetric model, meaning that both these compartments are isotropic. It could often get confused with one another. The stability is highly dependent on where you start, like how you initialize the model. And it has multiple issues, such as it has a flat objective function surface. It is hampered by noise, like noise can push you away from the optimal minima of optimization. It has an infinite solution space, which we will look at in the next slide. And it is bimodal, meaning that there are two solutions, right? So if the D star and the D, that is the perfusion and the diffusion, come very close to one another, then the model will not be able to distinguish which one belongs to diffusion and which one belongs to perfusion. And this has actually been shown in multiple papers in the past. Here, one of my favorites is Novikov's paper called On Modeling, and by Dr. Jelesu. on the degeneracy. They don't talk about IVIM in that particular paper, but the effect is seen in this type of modeling too. So this basically requires a better type of optimizer, and that I'll talk about in the next slide. So before we get into the optimization scheme, this is what we will be using. It's called the variable projection method. So what variable projection means is that in this model of IVIM, where you have the bi-exponential, like you have to estimate the F, you have to estimate D star and D. Let's take the standard IVIM model, for instance. So these are the three parameters that you want to estimate, right? And the idea is that we want to separate this F from the D and D star. So disentangle the Fs, the volume fractions, first estimate them separately, and then estimate the D and D star. And that should help with optimization. So basically, variable projection implies projecting them into a subspace, the parameters into their own separate subspaces, where the optimization is a little simpler and it will always converge to a better minimum. This was proposed by Golub and Pereira back in 1973. We have been working with this method with Hamza Farooq, who first proposed it for microstructure imaging of crossings back in 2016. So basically, you take all the, like it should work for every type of model. But for IVIM, let's say you had S1 and S2, the two compartments. You would compute a Moore-Penrose pseudo-inverse like you do for linear regression. And then using the pseudo-inverse, you estimate the F first, okay? You project basically the signal, like you project that particular part of the equation onto the signal, and you use that to then minimize objective cost function. So this is known as the variable projection function. As you can see, first we had the F and the X both in this equation. And then after doing this variable projection, it is just an equation in terms of X. So we have basically eliminated F by optimizing, by estimating it separately in a previous step. So this is a very nice trick, and like the general alternative to doing this is using Gauss-Newton type of optimization, like Leavenworth-Marquardt algorithms. And what that does is basically computes a local Jacobian, and that Jacobian basically tells you which direction to go into, like is often done in SGD. So basically, in order to perform the optimization for the variable projection step that I mentioned in the previous slide, we will be using simplicial homology. Simplicial homology is a branch of topology that I have shown over here. It falls under algebraic topology and specifically computational homology. The optimizer that we will use will find all subdomains of the particular problem at hand, like of the optimization function. For here, I'm taking IVIM. Basically, it will return all local minima, and then we can try to understand which local minima is the correct one by setting constraints and stuff like that, which we will look at in the next slide. It is a global optimization method. So it does not work like SGD or like Gauss-Newton type of methods, where you try to compute a local Jacobian and then move forward with a step function, what is commonly known as trust region methods, but rather you do it all at once. The advantages that this type of optimization has is that it will return all local and global minima. It also returns the number of locally convex subdomains, and also like which can be used as a measure of multimodality. So for instance, in this case of IVIM, where we have perfusion and diffusion, it can help understand at what point is the perfusion getting entangled with diffusion and where is this degeneracy in estimation occurring. And it also detects neighborhoods where the local minima are. It extracts all the minima. So basically, if you feel that your model is not performing well, you can basically go to a particular voxel or to a particular region and see what is really going on. and it is not stochastic in nature. So a lot of optimizers which depend on computing local gradients basically are stochastic, meaning that they will not always end up in the same minima if they are initialized differently. So this also has that advantage that it will always result in the same solution. So this is how the SHGO algorithm works. So given your search space, that is your objective function, it samples points on that objective function, and then it basically creates a mesh of these n vertices by, like, you can think of it as a graph. That is in topology referred to as a simplicial complex. Then it performs a Sperner's lemma cluster. So Sperner's lemma basically gives you a way of numbering the vertices of the simplicial complex such that you can detect local clusters on that graph. And then from those clusters that you have detected, you basically get minimizer pools. Like, these minimizer pools basically are regions where there is the possibility of a minima. And then within those minima, you perform, within those minimizer pools, that is like regions of that graph, you perform a local minimization and you get your output. This will become clearer in the next slide. So just to give you a brief overview of how these things tie in together. Basically, you take your data input. Let's think of it as a voxel. Then for each voxel, you fit your model using the variable projection functional. And then you perform a SHGO step for the second time. So it's like a sort of like a bi-level optimization problem, not exactly bi-level, because in bi-level there is a reverse connection, but this is how we formulated the problem, and it has some advantages in optimization. So SHGO works via two key theorems. One is that it finds all local minima that I've shown in the previous slide. And second is that it will have a stability. So basically, you won't get like stochastic solutions every time when you run the algorithm. You will always converge in the same minimum. And these are the two theorems. I don't want to get into them right now, but if you're interested, you can pause the slide here and read them out. Essentially, one says that it is a guarantee on where the minima is. And the second is that one might say that if you sample more points, will the chances of a minima occurring increase? And the answer is no. And that is because of this theorem 2. And the theorem 2 states that after a point, no matter how much you sample, you will always converge in the same minimum. Okay, so here is the part where I wanted to show that for the IVIM models, that there are bimodal solutions or flat value solutions. So for example, if you see this side of this figure, these are the two minima detected by using SHGO. Here, you can see that these three star domains, like what we refer to as star domains, but here is one minima and here is the second minima. And this is the simplicial complex that was built. And like the black lines show the gradient, that is shown over here in 3D. This is one case where there are two plausible solutions and the model doesn't know which one to pick, right? And this is the value at which, so for instance, at D star 0.35 and D 0.3, you can see that the value more or less the model cannot distinguish between D star and D. And same goes over here when basically D is 0.002 and D star is set to 0, then basically your model has infinite number of solutions. And this is what is referred to as value solutions. Both cases are value solutions, but basically there are infinite, like anything that falls along this line of somewhere between 0.001 and 0.002 would be a plausible value for diffusion. So this is another effect that you will see in bicompartmental models. So what one can do is essentially set constraints where you like whatever model you choose. For here I have showing IVIM again, since this presentation is focused on IVIM. You can set constraints, and you can basically get improved solutions. Already from the first row that I'm showing over here is using variable projection and SHGO. The second row is after adding constraints, after looking at the simplicial complex and looking at where the model is really failing, and the optimization improves significantly. So for D star, where the value of the Pearson's correlation was around 0.225, it goes to 0.87. This is a test-retest analysis where you have two sets. One corresponds to, like they are both the same patient, and the test-retest reliability basically increases, is what I'm trying to say. Okay, now let's take a look at real data. So here I have three different, I have two different subjects with 5 different methods. So this is the standard way in which people model IVIM, where basically they say that if I have like an exponential signal, then the first, like whatever corresponds to perfusion is estimated with a linear function separately, and then whatever corresponds to diffusion is estimated separately, and then is put into a Gauss-Newton type of optimizer that is non-linear least squares. So that is what segmented corresponds to. Bayesian is a Bayesian formulation of for solving this IVIM. Then one is with plain SHGO. Then the second is, the fourth is with mix. And the fifth column corresponds to the method that we are proposing. As you can see that the perfusion maps with both segmented Bayesian look very noisy, meaning that often what happens is that the model gets biased towards the diffusion, where the model looks more or less correct, but then the perfusion is misestimated and it looks extremely noisy. But with TopoPro, that is the method that I just described, the perfusion map along with the diffusion map both look really good. I will show the error plots on the next slide. In both the cases, like both these data sets, it looks really nice. So the first data set that I'm showing has 21 gradient interactions, and the second one has 49 gradient interactions. And these are the slice numbers that I'm showing over here. As you can see that the model is also very highly dependent on the number of B values that you acquire at a smaller B value, at a smaller range. Like for example, how many B values you had less than 1,000 or 500 are really important for estimating IVIM, and that is a research field of its own. Here are some results with simulated data. So this is the ground truth of what we are trying to estimate for the perfusion, and the perfusion fraction F, and this is the perfusion coefficient. Like you can see that using TopoPro, as the SNR increases, so we have SNR 5, 10, 20, and 50. It is quite noise tolerant, and you get closer to ground truth as the SNR increases. But for these other methods, the perfusion fraction is not estimated properly. Often there is overestimation, or it is like underestimated by some of these methods. So for example, if you see that the segmented shows really good performance as SNR 20, 50, and 10, but then the perfusion fraction estimated by them is really wrong. Everything is just basically noisy, right from SNR 5 to SNR 50. And then I have also quantified these results with bar plots. As you can see that TopoPro, which is shown in red, has much smaller error as compared to all other methods for estimating the perfusion coefficient. Same goes for perfusion fraction. Sometimes the perfusion fraction estimated by the segmented method is really good, but that is due to the bias. And with SNR, like here is an average plot. The TopoPro method does really well. All right, this is what I wanted to say about the IVIM modeling and its optimization. Now let's take a look at the implementation.